So, welcome to lecture series on advanced linear algebra. We have discussed if V and W be two vector spaces over the field say capital F, and if V and W both are finite dimensionals of dimension say n and m respectively, then we have seen LVW, that is collection of all linear transformation from V into W, is a vector space of dimension Mn. So, this we have proved it by theoretically constructing Mn number of linear transformation from V to W and showing that they are linearly independent and span the space LVW. Let me take an example. Let V equal to set of all 3 cross 1 column vectors, that is F3 cross 1, and W equal to set of all 2 cross 1 column vectors. We know both of them are vector spaces over the field capital F. Now, so the dimension of LVW is equal to 3 into 2 is equal to 6. Let me construct the corresponding linear transformation from V to W. Okay. So, now we want to construct 6 linear transformation from V into W, which will span the space LVW. So, consider following 6 linear transformation from V into W based on the order basis B, which is equal to, let me consider 1 0 0, that is transpose, then 0 1 0 transpose, and 0 0 1 transpose. This is one order basis of V, and B prime is equal to, let me consider, so beta 1 equal to 1 0 transpose, and beta 2 is equal to 0 1 transpose. So, let me consider this is my alpha 1, this is my alpha 2, and this is my alpha 3. So, for order pair PQ, okay, so 1 less than equal to P less than equal to 2 and 1 less than equal to Q less than equal to 3. I am defining EPQ is a linear transformation from V to W as follows. So, E1 for any alpha belongs to V is equal to, let me define, it is like this: 1 0 0 0 0 0, this into something alpha. Okay. So, alpha is basically my column vector please, and E 1 2 I am defining, E1 2 from V to W I am defining as an alpha goes to something like 0 1 0 0 0 0 into alpha. E1 3 I am defining again alpha goes to 0 0 1 0 0 0 alpha, and E 2 1 mapping from V to W is like this. Alpha goes to basically 0 0 0 1 0 0 and alpha. Then E 2 2 defining by exactly alpha goes to 0 0 0 0 1 0, this one, and E 2 3 is defining as alpha goes to 0 0 0 0 0 1 operating on alpha, please. So, I have considered 6 linear transformations E1, E11, E12, E13, E21, E22, E23 as like this. So, you may have the questions how to guess that E11 I have to define like this type of matrix. I mean, I can say suppose this is A11 alpha, then E1 to A12 alpha, A for E13, A13 alpha, like that. How to know this set of matrices, please? So, I will discuss this issue later on, but let me check does it satisfy my definition of the linear transformation the way we introduced in our theory. Okay. So, it has to be E11 operating on alpha 1 has to be equal to beta 1. Or let me check, E11 operating on alpha 1 is equal to how much? It is equal to 1 0 0 0 0 0, and we have 1 0 0. So, this is equal to simply 1 0. So, 1 0 means beta 1. So, E11 operating on alpha 1 equal to beta 1, but E11 operating on alpha 2 is equal to, it has to be 0, E11 operating alpha 3 has to be 0. So, let me check whether it is satisfying this condition or not. 1 0 0 0 0 0 operating on 0 1 0. So, this is equal to certainly having 0 0. Similarly, and E11 alpha 3 equal to, we can check this into 0 0 1 equal to again 0 0. So, you can check E11, E12, E13 and E21, E22, E23, they satisfied all the criteria of the linear transformation what we have defined there. So, we have 6 linear transformation from V into W, and one can show any linear transformations, any LT transformation T from V into W can be written as linear combination of this your E P Q 1 less than equal to P less than equal to 2 and 1 less than equal to Q less than equal to 3 place. Okay. So, this we can try in the home. Now, I am bit curious one thing. Suppose T is a linear transformations from V into W and U is a linear transformation from W into Z, where V, W, Z all are vector spaces over the field say capital F. Then what can you say about the multiplication of these two linear transformation, please? So, what is the question? Question is like this, say let T be a linear transformation from V into W and U be a linear transformation from W into Z, where V, W, Z are vector spaces over the field a capital F. We know when you use the composition as the multiplications, the composite functions T and U, it is again a function from V into Z. Here if I instead of simple function T, I am taking T is a linear transformation from V into W and U is a linear transformation from W into Z, then what can we say about the product functions ut, which is a function from V into Z, whether ut will be linear transformation or not. You can immediately check ut is also a linear transformations. Then ut is a linear transformation from V into Z. How? So, here ut operating on alpha is equal to u of t of alpha, please. So, this is the definition. Now, if I define like this, we have for any alpha beta belongs to V and C belongs to capital F, ut operating on C alpha plus beta, if I consider like this. This is equal to, we know, u of t of C alpha plus beta. So, this is equal to u of C times t of alpha plus t of beta, because t is a linear transformation. Since t is a linear transformation from V into W, so this property will holds good. So, this implies I can write down now T alpha is an element in W and U is a linear transformation from W into Z. So, this means I can write down this is equal to C times U of T of alpha plus U of T of beta, please. So, this means this is equal to C times I can write down u t of alpha plus u t of beta. So, this implies when we use the composition as a multiplications of two functions, then this u t is a linear transformation from V into Z, please. So, we see that even if I consider product of two linear transformation, it is also a linear transformations. If I write u t, the domain is basically mapping from V into Z, but if I write t u instead of u t, okay, let me check. See, V is V to W, it is my t, and if I consider u, that is W to Z. Is it possible to define T u? I mean first operating on u, I mean to consider u is a first function, then u is u basically the okay. So, T u is not defined, please, because T u operating on some beta belongs to W, u beta belongs to Z, but T is mapping from V to W. So, therefore, it cannot be defined linear operator. What is linear operator? When a linear transformations is defined from a vector space V into the same vector space, then it is a linear operator, please. Okay. So, let V be a vector space, the space over the field capital F. A linear transformation V into V is called as a linear operator on V. Okay. So, examples we can see like linear transformation, here also I can give. Let A is a say 3 cross 3 matrix over the field capital F. I mean to say the entries of A is from field capital F. So, now let me consider T is a function from F 3 cross 1 to F 3 cross 1 defined by say any element say x belongs to F 3 cross 1 column vector. This goes to, let me consider A x of 3 cross 1 order. So, we see that any C times capital X plus Y, if I consider when x and y belongs to F 3 cross 1 and C is any constant over F, then we see T of C of x plus y will be equal to A times your C x plus y. So, this is equal 8 operating on C x plus A y, which is equal to C times A x because C is a constant. So, A x plus A y. So, this is equal to C times T x plus T y. So, this implies T is a linear operator on F 3 cross 1. If I consider A is a 0 matrix, then also I will have another examples of a linear operators from F 3 cross 1 to F 3 cross 1, which is mapping any element to a 0 element of the F 3 cross 1, please. You can take another examples. Let V be the space of all real valued continuous function over say real line R. So, we know that V is again a vector space. So, consider T a function from V into V defined by T f for any real x, T of x equal to, let me define 0 to x f of t and dt. So, if I define like this, then I see that this function t is a function from V into V and it is also linear transformation. In fact, it is a linear operator because V equal to W, please. Now, let me go to these specific linear operators, I mean linear operator of finite dimensions. Let V be finite dimensional vector space, vector space over field capital F. Consider all linear operator LO on V. Let the set of all linear operator on V be denoted by LVV. Okay. So, it is basically set of all linear transformation from V into V. Let dimension of V be n. So, dimension of LVV will be equal to n square. According to our last results, here also one can construct n square linear operator on V, which will act as a basis for the space LVV basically. Okay. And this LVV is a vector space. This is already we have done. It is exactly same the way we did for the LVW also. So, I am not repeating that one. So, you can check it. So, it is a vector space and dimension of this space will be n square. See, in last result what we have proved, if T is a linear transformation from V into W and U is a linear transformation from W into Z, then ut is a linear transformation from V into Z. Now, if I consider V equal to W equal to Z, then I can say that here U and T both of them are basically linear operators on the vector space V please. So, U into T is defined, it will be again a linear operator on V please. So, apart from vector addition and scalar multiplication to LVV, if I consider multiplication of two vectors, here vectors means basically I am talking about the linear operator, then also we see that product of two vectors is again a vector type. This is basically my composition is multiplication as we used to do in the case of product of two function please. Apart from this vector addition and scalar multiplication on the LVV, if I add another binary operation that is multiplication of two vectors, then I can see okay, for any U belongs to LVV and identity function from V to V will be also in LVV, it is also linear operator. I also belongs to LVV. We have U into I equal to U, which is equal to I into U also. Second, for T1 and T2 belongs to LVV, for U belongs to LVV, we have U times T1 plus T2 equal to U T1 plus U T2. Also, T1 plus T2 into U equal to T1 U plus T2 U. Third, for any C belongs to capital F and U T belongs to LVV, C times U T C U T which is equal to U C T. We can quickly check that as we used to do in the case of the function, here also this the function u and t, here function not only function, it is a linear operator. With respect to composition multiplication, we see that distributive law over the addition also holds good, and we also see that there is this identity operator on LVB such that u into I equal to u is equal to I into u. So, we can quickly check that this type of results also holds good. I mean to say ut into ut1 plus t2 operating on any vector alpha will be equal to ut1 of alpha plus ut2 alpha, you can check it. Similarly, you can also check that other two this axiom of properties with respect to multiplication please. So, LVV along with multiplication of composition satisfies above three properties or axioms. With respect to multiplication composition satisfied above three properties axiom. A vector space when it satisfied above three properties or axioms, these are called as the linear algebra. Axioms called as linear algebra please. Okay, fine. So, LVV is a linear algebra. Okay, so let me conclude. So, what we have learned here? So, we have seen that what is linear operator, and similar to LVW, LVV is also a vector space, and if the dimension of vector space V is finite, say n, the dimension of LVV is n square, and in the vector space LVV one can also introduce multiplication compositions, and with respect to that composition it satisfied three more axioms, that is the existence of identity operators such that I into u is equal to u, distributive property over the addition also holds good, and one more that if we constant c and u and t are two linear operator, then c of ut is equal to c u and then t, or we can take the c inside also, I mean u into ct also. So, this type of characteristics or properties also holds good with respect to multiplication, and a vector set satisfying these three characteristics or property with respect to multiplication is called a linear algebra. So, LVV is a linear algebra.